Swayam Prabha. Digital India. Educated India.
So this is what our gradient descent algorithm was. We were running this for some 1,000 iterations, starting with some theta naught. And what we were trying to do is update the thetas using the gradient values. Okay. Now, instead of the single or the two weights w comma b that we had in our earlier toy example, now we have these many weights, and we want to compute the partial derivative with respect to all of them. So let's focus on one such weight, and I've deliberately taken one which is farthest away from the output, right? So your output is at the green layer, and I've taken a weight which is there in the input layer, which is W112, right? So the 1, 2 weight in the first layer, that means the 1, 2 entry of W1 matrix. So now to learn this weight using gradient descent, actually, not SGD, using gradient descent, we need a formula for the loss, partial derivative of the loss function with respect to this weight. Everyone agrees with this? If I give you this formula, then you can apply gradient descent. Is that fine? Everyone on board? Okay. So now we'll see how to compute this. So let's take the very simple case where we have a deep network, but a very thin network. What do I mean by thin network? I just have one neuron in every layer. I don't have these N or D1 neurons in every layer. I just have one single neuron. So it's a very thin network, but it's a deep network. Now in this case, suppose you wanted to compute the derivative of the loss function with respect to the first weight, which is W111. How would you do it? Does the loss function depend on W111? First of all, let's answer that question. The loss function was a squared error loss function. How does it depend on W111? Because the loss function depends on the predicted value, which is y hat. Y hat depends on AL1, which depends on A21, which depends on A11, which depends on X1. And how does it depend on X1? Via W111, right? So this is again a composite function of X, and this weight W111 appears somewhere in this composite function. Is it fine? Okay. So y hat is a function of X, and the loss function is a function of y hat because it computes the difference between y hat and the true value. So we have established that the loss function is a function of W11. But it's a very composite function. Now, if you have such a composite function, how do you compute the derivative? Everyone? Chain rule, right? So you can apply the chain rule. So can you apply the chain rule for this? Can you just see if this rule makes sense? Loss function with respect to y hat with respect to the last layer with respect to the previous layer, and so on. Does it make sense? Right? And each of these elements is going to be a simple function, right? Because h21 is related to a21 by the sigmoid function. So for simple functions, you know how to compute the derivative. If I ask you to compute the derivative of sin x, or even for that matter, sigmoid of x, we've already done that. So any of these individual elements you can easily do, right? But remember, this is a thin network. Things become much more complicated when you have a wide network, because then several relations exist, right? So let's look at that. So in this thin case, it's very clear, right, how it works. So now, starting with that, so let's still continue with this intuitive explanation, right? So what is happening here is now we have a deep and wide network, and we get certain loss at the output, and we try to figure out who is responsible for this loss. So give me that answer. Who is responsible for this loss? So we go and ask the loss that you are producing a non-zero value. What is wrong with you? Why are you not behaving properly? So we go and talk to the output layer, because the loss depends on the output layer. If there was a loss, that means the output was not correct. So we go and ask the output layer that why are you behaving like this? Why are you not producing the desired output? What is wrong with you? So what will the output layer tell you? I didn't do anything. I just took the output from the previous layer, did some simple transformation on that, and I gave you the output. So if I'm wrong, that means the previous layer was wrong. So go and catch that guy. Okay. So we continue with our investigation, and we go and ask the previous layer. Now the previous layer will again say that I take responsibility for my part, but I'm only as good as the hidden layer and the weights before me, right? Now, so it will say go and talk to the hidden layer before me and the weights before me. Now of these two guys, the hidden layer and the weights, which one has the responsibility? The weights. Because what is the hidden layer going to tell you again? I depend on the previous hidden layer and the weights. And this will happen all the way back to the input, right? So what will happen is, when she go and talk to W3B3 or WLBL in this case, WLBL will say, okay, we are responsible for the loss, but HL is again going to redirect you to the previous layer. So if we continue our investigation in this manner, which are the guys which are going to be responsible? All the weights and all the biases. Is that fine? Now, it's okay in English to say that the weights are responsible, hence they should change their behavior and improve so that we get a better loss function or we get a lower loss function, lower loss value. But how do we compute this responsibility? How do we compute this responsibility? So you get my question? All of us agree that in English, this statement is fine, that the weights and biases need to take responsibility and improve themselves so that the loss is reduced. But what do we mean by responsibility? How responsible is a weight for the given loss value that you have? How do you compute this responsibility? Take a guess, because there are not many things that we have learned so far, right? So take a guess.
So the more important the feature is, the more responsible is the weight.
How do you compute that? So suppose, let me ask you this question. If there is a weight which is very important, okay, and it could really change the loss value by a lot. If I change this weight value by a small amount, what would happen to the loss? Change a lot. Change in weight, a lot of change in the loss. What is this quantity? It's the partial derivative. If I change W by a small amount, I will see how much does the loss change. And this quantity tells me how responsible is this weight towards the loss. Everyone gets that? That's what the derivative tells us. If I change the quantity by a small amount, how much does the output change? And that's exactly what we are trying to do in gradient descent. We're computing this gradient, right? So the derivative tells us how responsible this weight is towards the loss function, right? So that's why we are going to compute this derivatives. But the problem is that if I want to compute the derivative of the loss function with respect to a weight which lies in the first layer, how do I compute that, right? That's a very long composite chain that you have, and you have to traverse this chain, right? So what we were trying to do in this investigation is that we wanted to compute the quantity on the left-hand side, which is the derivative of the loss function with respect to one of the weights in the first layer, right? Which is very far away from the loss function, right? It's almost like a butterfly effect, right? You change something small here, and the loss changes drastically, and you need to trace this effect, which is going to be hard. So instead of talking to the weight directly and asking it what's wrong with you, we'll go towards it step by step. So we'll first talk to the output layer, and basically what we're doing is we are applying the chain rule. We'll first talk to the output layer, then talk to the previous hidden layer, then talk to the previous hidden layer, and finally talk to the weights. And this, whatever I am saying in English, what do you call it mathematically? What are you applying here? You're applying the chain rule, right? So that's exactly what backpropagation means. You need to propagate the loss all the way back to the weights in your initial layers, or for that matter, any layer in your hidden neural net, in your deep neural network, right? So this propagation of weights is called backpropagation, and the key again is derivatives, and in particular, you'll use the chain rule of derivatives. Is that fine? Everyone gets that? So that's where the chain rule comes into picture, and this is what you need to figure out. How do you compute the derivatives with respect to the output layer, the hidden layer, and all the way back to the weights? And intuitively, what you need to understand here is that each of these quantities which I have put inside the curly brace, each of them individually is easy to calculate, right? Because these are simple functions. These are not very deep composite functions. And I have a set of derivations in my lecture notes where I compute each of these in detail, so you can go and take a look at them. But for now, if you understand this at an intuitive level, that's enough for me, right? So everyone gets this, what backpropagation does. It tries to compute the gradient partial derivatives of the loss function with respect to each of the parameters. And although it looks a bit daunting, you can easily do it once you break it down into the chain rule and compute one step at a time, right? Now, can you tell me something more interesting here? Suppose instead of computing the derivative of the loss function with respect to W11, Suppose I wanted to compute the derivative with respect to W112. What would happen? Can I reuse any of the computations that I had done for W111? The chain rule is going to stay the same up to a certain portion, and only the last part is going to change, right? So that's another interesting thing. So although you think that you have many parameters in your network, a lot of computations while computing the partial derivatives can be reused, right? The initial portion of the chain can be reused when you just change the last weight element in the last weight matrix. Is everyone fine with that? Okay. So then applying backpropagation. So what I've done is I've given you an intuitive explanation for computing the partial derivative with respect to any parameter in your network. And all of us had agreed that if I tell you that, then you can go back and apply gradient descent and update the weight of, update that particular parameter in your network. So is that fine? So now you can extend the gradient descent algorithm to work for all the parameters in your network with this partial derivative computation. Is that okay? Everyone is fine with that? Okay. So that's where we'll end this discussion. And we'll go on to the next lecture, which is about convolutional neural networks. So what I've done so far is we started with a simple sigmoid neuron, and I was calling it a shallow neural network. From this simple sigmoid neuron, first thing that we've done is, even in this simple case, how do we learn the parameters of this simple sigmoid neuron? And we saw that we can use the gradient descent algorithm for that, and we principally derived it. We came up with the principal method of ensuring that we iteratively learn the weights such that at each iteration, the loss function decreases and hopefully reduces to 0. Okay? And we came up with that update rule for W and B. And then we argued that we could have just written it as a single update rule where W comma B is treated as a vector theta. And we came up with the update rule for theta. Then from there, we graduated to a deep neural network where your output was a very complex composite function of your input. But we could still write it down exactly. And when we wrote it down, we saw that there were actually many parameters in this network. But then we argued that just as you had theta is equal to W comma B, you can have theta is equal to all these parameters on this network. And we actually enumerated all of them in that large matrix that we had seen. And that entire matrix, you could think of it as one large vector. So that's one large theta that you have. And now you need to update theta as theta is equal to theta minus eta into the partial derivatives of all these elements. And those partial derivatives are nothing but if you put them all together, you get the gradient. And then we saw that if you want to compute the partial derivative of the loss function, you basically first need to define what the loss function is. And to define the loss function, you need to first decide what is your output function going to be. So we defined the loss function and the output function for two different class of problems. One was regression and the other was classification. And we came up with this linear squared error loss and softmax cross entropy loss, right? And now once we had that, we have the loss function. That means we can compute the first quantity there because now we know where to start the chain. And then we argue that by applying the chain rule, you can compute the partial derivative with respect to any parameter in your network. And once you have that value, you can use the same gradient descent update algorithm for all the parameters in your network. Okay? So in effect, we now have a recipe for training a deep neural network. Is everyone fine with that? Okay. So now let's move on to the next lecture.